Evaluation using antiderivatives. Now, in the sections we've just covered, we really dug into what a definite integral is. We looked at it as the limit of a sum, essentially adding up infinitely many rectangles to find the area under a curve. That approach is fantastic for building a solid understanding of the concept of the definite integral and visualizing what it represents. However, as you can imagine, actually calculating an integral that way, finding that limit of a sum, can be incredibly time-consuming and prone to errors. Thankfully, there's a much more efficient method. We can evaluate definite integrals using something called antiderivatives. You'll recall from your earlier work that an antiderivative is a function whose derivative gives us back the original function. And this new method, this shortcut, is all based on a really important result in calculus called the fundamental theorem of calculus. We'll be exploring exactly how this theorem lets us connect antiderivatives to definite integrals in the slides that follow. So, get ready to see how we can move from tedious calculations to a much more streamlined process. Okay, so let's move on to a much more practical way to calculate definite integrals. Understanding the concept. Here, we're setting up the core idea. If we have a continuous function, and I'm writing that as f of x on a specific interval, which we denote as a to be, and if we can find another function, let's call it f of x, such that the derivative of f of x is equal to our original function f of x, then f of x is what we call the antiderivative of f of x now. Here's the key connection to definite integrals. Instead of calculating that limit of sums, we can simply find the difference in the values of this antiderivative, f of x, at the upper and lower limits of our interval. Let me show you what that looks like mathematically. We have the integral symbol, and then we write a as the lower limit, b as the upper limit, then f of x, and finally dx. This whole expression, integral from a to b of f of x dx, represents the definite integral. And according to this principle, it's equal to f of b minus f of a. Let's break down what each of these parts means. That integral symbol with the limits and the function, integral from a to b of f of x dx, is, as we've discussed, the definite integral of the function f of x, evaluated from x equals a to x equals b f of x, as we just covered, is the antiderivative of f of x. Meaning, if you take the derivative of f of x, you get f of x. A represents the lower limit of integration, the starting point of our interval on the x-axis. And b is the upper limit of integration, the ending point of our interval. Okay, so let's dive a little deeper into how we actually calculate definite integrals using antiderivatives. Remember on the previous slide, we talked about how finding the area under a curve using limits and sums could be quite tedious. Well, this slide explains the much more efficient method. Keep this slide in mind, because we'll be using this formula repeatedly in the following slides as we work through examples. We'll see exactly how to find those antiderivatives and apply this formula to calculate definite integrals. Step-by-step evaluation process. Okay, so now that we understand why we can use antiderivatives to evaluate definite integrals, thanks to the fundamental theorem of calculus, as we discussed on the previous slides, let's break down how to actually do it. This slide outlines a clear, step-by-step process. To evaluate a definite integral using antiderivatives, follow these manageable steps. Think of this as a recipe. If you follow the steps in order, you'll get the correct answer. Step 1. Find the antiderivative. This is the crucial first step. We need to find a function, let's call it f of x, that undoes the function we're integrating, f of x, remember. Finding the antiderivative is exactly what we practiced when we was doing indefinite integration. So the techniques are the same, power rule, substitution, and so on. The key here is to temporarily ignore the limits of integration, those a and b values we've been talking about. We're just focusing on finding the general antiderivative at this stage. Step 2. Notation of limits. Once you've found your antiderivative, f of x, we use a specific notation to show we're about to evaluate a definite integral. We write the antiderivative inside square brackets like this, bracket f of x bracket close. Then, we place the upper and lower limits of integration at the right end, written as a superscript and subscript respectively. So it looks like this. F of x with a subscript a and a superscript b, we write it as f of x evaluated from a to b. This notation is just a shorthand way of telling us we're going to evaluate the antiderivative at the upper and lower limits and find the difference. Step 3. Substitute the upper limit. Now we start using those limits. We substitute the value of the upper limit, which is b, into our antiderivative, f of x. This gives us f of b essentially. We're finding the value of the antiderivative at the upper boundary of our integration. Step 4. Substitute the lower limit. Next, we do the same thing with the lower limit, a. We substitute a into the antiderivative, f of x. To get f of a, this gives us the value of the antiderivative at the lower boundary. Step 5. Calculate the difference. Finally, and this is important, we subtract the value of the lower limit from the value of the upper limit. That is, we calculate f of b minus f of a. This difference, this numerical value, is the value of the definite integral. Remember, definite integrals give us a number, representing the area under the curve, or in the case of our physics example on the next slide, the displacement. So, to recap, integrate to find the antiderivative, then evaluate that antiderivative at the upper and lower limits, and finally, subtract the lower limit value from the upper limit value. That's the core process, and we'll see it in action with some examples on the following slides. Real-world application example, physics displacement. This slide presents a scenario involving physics, specifically motion. We're told that a particle is moving along a straight line, and its velocity is given by the function v of t equals 3t squared meters per second. Remember, velocity is the rate of change of position. Our goal is to find the total displacement of the particle between time t equals 1 second and t equals 3 seconds. Now recall that displacement is the change in position. And, as we learned earlier, the definite integral represents the accumulation of a quantity over an interval. In this case, we can find the displacement by integrating the velocity function over the given time interval. So, to set up the integral, we write the definite integral of the velocity function, v of t, from the lower limit of 1 to the upper limit of 3. This is written as the integral from 1 to 3 of 3t squared dt. dt simply represents an infinitesimally small change in time and is crucial for the integration process. Next, we need to find the antiderivative of 3t squared. Remember from our earlier discussions, the power rule for integration states that the integral of x to the power of n is x to the power of n plus 1 divided by n plus 1. Applying this to our problem, the antiderivative of 3t squared is t cubed. So, we denote this antiderivative as f of t equals t cubed. Now we apply the limits of integration. This is where the fundamental theorem of calculus really shines. We write the antiderivative, t cubed, within square brackets with the limits of integration at the right. This gives us t cubed evaluated from 1 to 3, which we write as t cubed from 1 to 3. Finally, we substitute the upper and lower limits into the antiderivative and subtract. First, we substitute the upper limit, 3 into t cubed, which gives us 3 cubed, or 3 times 3 times 3, which equals 27. Then we substitute the lower limit, 1 into t cubed, which gives us 1 cubed, or 1 times 1 times 1, which equals 1. Subtracting these values, we have 27 minus 1, which equals 26. Therefore, the total displacement of the particle from t equals 1 second to t equals 3 seconds is 26 meters. This demonstrates how the definite integral, evaluated using antiderivatives, allows us to solve a practical problem in physics. Okay, so now let's look at how we can apply what we've learned about evaluating integrals using antiderivatives to a real-world problem. As we discussed in the previous slides, finding the definite integral isn't just a mathematical exercise, it has practical applications. In the next slide, we'll work through another example, this time purely mathematical, to further solidify your understanding. Mathematical example. Okay, let's work through another example to solidify our understanding of evaluating definite integrals using antiderivatives. This one is a bit more involved, combining multiple terms. Here's the problem. We need to evaluate the definite integral of 4x cubed minus 2x with the limits of integration from 1 to 2. Now, let's follow the steps we just discussed. Step 1. Find the antiderivative. Remember, we temporarily ignore the limits of integration at this stage. We need to find the antiderivative of 4x cubed minus 2x. We'll do this term by term, using the power rule for integration, which states that the integral of x to the power of n is x to the power of n plus 1, all divided by n plus 1. Let's start with 4x cubed. Applying the power rule, we increase the exponent by 1, giving us x to the power of 4. Then we divide by the new exponent 4. This simplifies to x to the power of 4. Next, we have negative 2x, which is the same as negative 2x to the power of 1. Applying the power rule, we get x squared, and dividing by 2 gives us just x squared. Therefore, the antiderivative, which we'll call f of x, is x to the power of 4 minus x squared. Step 2. Notation of limits. Now that we have the antiderivative, we write it with the limits of integration correctly notated. This means we write f of x within square brackets and place the limits of integration at the right. So, the integral becomes x to the power of 4 minus x squared, with the limits 1 to 2. We write this as bracket, x to the power of 4 minus x squared, bracket closing, with a small 1 below and a 2 above. Step 3. Substitute the upper limit. Next, we substitute the upper limit, which is 2, into our antiderivative. So, we have f of 2 equals 2 to the power of 4 minus 2 squared. 2 to the power of 4 is 16, and 2 squared is 4. Therefore, f of 2 equals 16 minus 4, which simplifies to 12. Step 4. Substitute the lower limit. Now, we substitute the lower limit, which is 1, into our antiderivative. So, we have f of 1 equals 1 to the power of 4 minus 1 squared. 1 to the power of 4 is 1, and 1 squared is also 1. Therefore, f of 1 equals 1 minus 1, which simplifies to 0. Step 5. Calculate the difference. Finally, we subtract the value of the lower limit from the value of the upper limit. That is 12 minus 0, which equals 12. Final result. Therefore, the definite integral of 4x cubed minus 2x from 1 to 2 is equal to 12. And that's our final answer. Remember, the result of a definite integral is a numerical value, representing the area under the curve between the specified limits. We'll continue to practice this process, and in the next slide, we'll discuss some common mistakes to avoid. Common mistakes to avoid. First, let's talk about the constant of integration, often denoted as c. You might remember from indefinite integration that whenever we find an antiderivative, we always add plus c to the end because the derivative of a constant is 0. Many students then wonder, why don't we include this c when we're evaluating definite integrals? Well, the reason is that it actually cancels out. Let's say our antiderivative is f of x plus c. When we evaluate the definite integral, we calculate f of b plus c minus f of a plus c. Notice that the plus c and c terms cancel each other out, leaving us with simply f of b minus f of a. Therefore, for the sake of simplicity, we omit the constant of integration when dealing with definite integrals. It doesn't affect the final answer, so we don't need to write it. Next, a very common error is reversing the limits of integration. Remember, when you found your antiderivative, f of x, you need to subtract the value of the antiderivative at the lower limit from the value at the upper limit. That is, you calculate f of the upper limit minus f of the lower limit. If you accidentally do f of the lower limit minus f of the upper limit, you'll end up with the wrong sign on your answer. It's a simple mistake, but it can easily throw off your result. Finally, be extra careful with arithmetic when dealing with negative limits. If your lower limit, is a negative number, pay close attention to the signs when you're performing the subtraction. For example, let's say you calculate f of a and get negative 5. Then, when you evaluate f of b minus f of a, you're actually calculating f of b minus negative 5. Remember that subtracting a negative number is the same as adding a positive number, so this becomes f of b plus 5. It's easy to make a sign error here, so double-check your work, especially when negative numbers are involved. Okay, let's move on to slide 6. This slide highlights some common mistakes students make when evaluating definite integrals using antiderivatives, and it's good to be aware of these before you encounter them in your practice problems. So, keep these 3 points in mind as you practice, and you'll avoid some of the most common pitfalls in definite integration. Now, let's move on to the final slide, where we'll summarize the key takeaways from this entire section. Key takeaways. First, remember that the fundamental theorem of calculus is the cornerstone of this entire method. It's what allows us to bypass the often complicated process of finding the limit of Riemann sums. That's what we discussed way back at the beginning, and instead use the much more manageable technique of finding antiderivatives. So, instead of adding up infinitely many tiny rectangles, we find a function whose derivative is what we started with. Next, let's look at the formula. We have the integral symbol, then a to b. These are our limits of integration. Then f of x dx, representing the function we're integrating with respect to x. This whole expression, written as integral from a to b of f of x dx, is equal to f of b minus f of a here. F of x represents the antiderivative of f of x, so we evaluate the antiderivative at the upper limit b and subtract the value of the antiderivative at the lower limit a. Now, this is a crucial point. The result of a definite integral is always a single number. It represents the area under the curve between those limits, a and b, and area is a numerical quantity. Don't expect to get another function as your answer. You should always end up with a unique numerical value. Finally, let's quickly run through the steps one more time to make sure it's all crystal clear. The process is straightforward. First, integrate, find the antiderivative of the function. Then, substitute upper limit, plug the value of b into your antiderivative. Next, substitute lower limit, plug the value of a into your antiderivative. And finally, subtract the result of the lower limit substitution from the result of the upper limit substitution. Okay, let's recap everything we've learned about evaluating definite integrals using antiderivatives. This is our final slide, and it's all about solidifying the key takeaways. If you follow these steps consistently, you'll be able to confidently evaluate definite integrals using antiderivatives. Remember to practice, 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 and you'll master this technique in no time.